Hi, and welcome to Concept Based. I'm John Hepworth, and today we're doing a question on a new topic. We're starting permutations and combinations. Doesn't have any subtopics in it. This the whole section is permutations and combinations. And the first dot point in this talks about this notation of n exclamation mark. And so I've done a question here that involves simplification, which you can have appear in these permutations and combinations, have fractions in them. So, as is always the case when I talk about concepts of questions, as we're delving more into these extension one style topics, more and more of these fractions, these algebraic fractions come up. So, if you are struggling with fractions in any way, go back to your year 10 path content and review algebraic fractions because it's only going to get harder to do these fractions when you now have factorials in them. So, just make sure you've got everything down pat in that area first. All right, so let's have a look at this question. So if you haven't seen factorials before, this could look very strange. So n plus 4 exclamation mark, which we state is a factorial, minus 6 lots of n plus 2 factorial over n plus 3 factorial minus 2 lots of n plus 2 factorial. So first things first, what does this factorial mean? So if we were to break that down into a basic and just start with n factorial means that if n is an integer, it actually is multiplying itself by every number below itself. So we start off by multiplying by n, and then we need to multiply by a number 1 less than n. And so we can write that as n minus 1. And then we would multiply by another number less than n, which would be n minus 2, and so on until we get down essentially to 1. We're obviously not going to multiply by 0, or n plus 1, n factorial would equal 0. So it just goes down to 1. So if this was a numerical example and I said 5 factorial, it would just be 5 times 4 times 3 times 2 times 1. We would get the solution for that, which is 120. Okay, but generally we're not dealing with numerical examples when we're doing these types of permutations and combination questions. We're just going to have an n variable in there all the time. So we have to know this expansion here, this n factorial expansion. So then we're now going to apply that to this fraction question. Now, when you're attacking these algebraic fractions, there's probably three things you need to take into consideration. If it's a cross multiplication, we're looking to simplify in our cross multiples. If it is a single term in the denominator, we might want to break the fraction up. But if it's one like this, where we have two terms in the denominator and we can break the fraction up, but it doesn't help us, then what we're probably looking for is factorization. And there's a real key in these factorials when you're doing a factorization is you always try and make the big one look like the little one. That's the concept that I try and teach kids all the time. Big one looking like the little one. That is just the approach we use because we can modify them. Now, sure, if there are students out there that feel really comfortable with these, yes, you can modify the small one to look like the big one. It usually results in a bit more algebra. So we typically would just go with make the big one look like the little one. So let's look at this question. What's the big one and what's the little one? So n plus 4 factorial is bigger than n plus 2 factorial because n plus 4 factorial would be, well, actually, let's write it out so we can have a good look at that. So n plus 4 factorial is n plus 4 times n plus 3 times n plus 2. Actually, I don't need to write that times n plus 2. And then it keeps going. And what we have to notice is that when it keeps going here, there's a little trick we can use. We could actually chop this off right here and note that we've got n plus 4, n plus 3, but everything below that little squiggle that I've drawn there is actually n plus 2 factorial. It does n plus 2 times n plus 1 times n minus 1 and so forth. So we can actually write n plus 2 factorial at the back here. And we've changed this big one, n plus 4 factorial, into a little one, n plus 2 factorial. It just comes with these additional algebraic terms, n plus 4 and n plus 3. But we can make that modification because we want the terms to look like each other because we're going to factorize. Of course we're going to factorize. That's how we're going to simplify. So now let's attack this specific question using that little example I just gave there. Let's look at how we can write the numerator. So the numerator, we can write n plus 4 n plus 3 times n plus 2 factorial. That replaces the n plus 4 factorial minus 6 lots of n plus 2 factorial. On the bottom, we're in the same sort of situation. We've got an n plus 3 and an n plus 2, so we're going to make the n plus 3 look like the n plus 2. So again, we're going to change that to be n plus 3 times n plus 2 factorial. I've used that same process. N plus 3 factorial is n plus 3 times n plus 2 times n plus 1 and so forth. But I've chopped it off at the n plus 2 and rewritten it as a factorial. Now we're minusing 2 lots of n plus 2 factorial. Okay, so now we've got everything in the same term in terms of factorials, which is what gives us the opportunity to factorize. Because essentially we could replace n plus 2 factorial with x, and we're just taking the x out. So we just take the same approach as what we normally would do in our factorization, and we take n plus 2 factorial out of the top, and we're going to be left with the n plus 4 and n plus 3 from the first term. And in the second term, the n plus 2 factorial comes out and just leaves us with the 6. And then down the bottom, same process. We're going to take n plus 2 factorial out. And that's going to leave us with n plus 3 and minus 2 in the bottom there. And just like any algebraic term, we can cancel n plus 2 factorial out from the top and bottom here, so we do so. Now it's worth noting here that these factorials are never going to equal 0, like n will never equal -2 to make the bottom of this fraction equal 0, which obviously would never work because n is a positive integer. So, it's just 1, 2, 3, 4 it could be. So that's the only way that the factorials in these types of permutations and combinations are going to work. So now we've simplified down and we're left with n plus 4, n plus 3, minus 6 over n plus 3 minus 2. And we are back in year 10 algebraic fractions land. And we just go ahead and use all the tools that we've used before. So this bit at the top here is the extension 1 part. And then it just comes into normal algebraic fractions. But they love asking questions where you then have to use tools that you've learnt historically to do these types of questions. And that is that we have to simplify quadratics. So we expand this top one and we get n squared plus 7n. It's going to be plus 12, but then I have to minus 6. Because that minus 6 is up there. So plus 12 minus 6 is just going to give me plus 6. And then that's over n plus 3 minus 2 is n plus 1. And now we factorize that quadratic. And so we're looking for two numbers that multiply to give 6 and add to give 7, which is 6 and 1. And we get n plus 6, n plus 1 over n plus 1. And then, of course, we can cancel that n plus 1 off the bottom with this n plus 1 at the top. And we are just left with n plus 6, which is super wild that you could go up to this part of the question and put any value in for n, let's say 10, and go and do all of this on your calculator. Yeah, there's a factorial button on your calculator. It's X, exclamation mark. And you would get out 16 because it's always going to be n plus 6. So if n was 10, it would be 16. So it reduces down significantly. And this helps us in future permutations and combination questions when we're trying to find out how many ordered selections there are and so forth. So again, the rule or the concept, I think that makes it super easy is make the big one look like the little one. And if you're struggling with algebraic fractions, revise that content first before having a crack at these types of simplifications again.